Okay, we are recording. So good morning, everyone. What we're going to do today is we're going to get into section 13.4, which is motion in space. So this is space curves. We're now thinking of these parameterized curves as the position that a particle is obtaining at a particular time. And so we can think of these parameterized curves as now the trajectory or the path of motion for a particle. And now with the notion of a derivative and a second derivative, we can talk about velocity and acceleration. And then we'll see that acceleration can really be broken up into two parts. So a motion of a particle, when we just consider its acceleration or how its velocity is changing, it can be broken up into two parts: a tangential velocity and then a tangential acceleration, and then an acceleration in a different direction, what we'll call the normal acceleration, and we'll see how to calculate those. So I'm just going to introduce the terms that we're going to use in this section. And so the first term is the velocity vector. And this is, the velocity vector is just our good old derivative of our vector valued function. So if r of t we're now thinking of as the position of a particle at time t, then its derivative, or the rate of change in its position, is its velocity. So the velocity vector is the derivative of r. And then the speed of a particle, that's the magnitude of the velocity. In the past, when you've mostly been dealing with particles moving in 2 dimensions, then the speed has been, in some sense, well, actually, even in 1 dimension, when you imagine it moving just back and forth along a line, a particle moving back and forth along a line, then its speed is in some sense just it's the magnitude of the velocity, but it was in some sense just you strip the sign away and you get the speed. Whereas now we're in space and our velocity vector can be pointing in any different direction as it moves along. It's just pointing where the particle's going. And the magnitude of that is what we call speed. So it's the magnitude of our velocity vector. And one thing we're going to do with this is we are going to split our velocity vector into its magnitude and its direction. So its magnitude is given here as its speed, and its direction is what we'll introduce on the next page, which is the unit tangent vector. And then from that, we can get the acceleration. So the acceleration is just the derivative of the velocity, as usual. But since the velocity was the derivative of the position function, then acceleration is the second derivative of r. Okay, so those are our ideas. Now, r is the position of a particle, its derivative is velocity, and its second derivative is acceleration. So let's go ahead and work out an example. So suppose the position of a particle is given by this parameterized curve, r of t. We want to find its velocity, its speed, and its acceleration, all at a given time, t equals 2. So we'll first work it out in general. We'll work it out for an arbitrary time t. So the first thing we're going to want to do is find its derivative. So this is our velocity. Maybe I'll just jot that down, and I'll move this over just a little bit. Fire in v of t. And what is that? That is the derivative of the first function, the exponential. That's 2e to the 2t. The derivative of the second, which is the square root of t, is 1 over 2 root t. And the derivative of the third function, which is 1 over t squared plus 1, I'll just think of 1 over t squared plus 1 as t squared plus 1 to the negative 1. Because if I think of it like that, then I don't have to use the quotient rule. I can just use the chain rule with the power rule. And so this becomes a negative 2t over t squared plus 1 all squared. Okay, so that's our velocity function, or velocity vector, if you will. Now we want to find the acceleration. So the acceleration is going to be the derivative of the velocity. And so we go ahead and differentiate again. That's 4e to t. This is going to be 1 over 4t to the 3/2. And the derivative of this last bit here, we'll use the quotient rule. So it's the derivative of the top, -2, times the bottom, minus the top, which is plus 2t, times the derivative of the bottom, which is 2t squared plus 1, times the derivative of the inside, which is the 2t. Looks like I'm having problems at the boundary here. So I'm just going to move it over a little bit, sort of hiding what's going on the boundary. Okay, there we go. I'm getting too close to the edge of my paper, it seems. I'm going to have to move it over again. It's not letting me write on the far right. There we go. Get that closing bracket in here. There we go. And then the denominator, okay, so we've done the the quotient rule. So it's t squared plus 1 squared, all squared. So the denominator all squared. So that's to the power of 4. Okay, so now we'll simplify this just a little bit so we can work out some values. So this is 1/4. I'll put it as t to the -3/2. And what does our top become? Well, I've got a t squared plus 1 factor in each of the terms in the top, so I can cancel one of those off. I can get rid of one of those, and I can get 3 of them down below. And so that gives me a -2t squared plus 1. And then I get plus 8t squared, and that's all over t squared plus 1 cubed. And this can simplify a little bit further. What does it become? We've got a -2t squared, we've got an 8t squared, so that gives us a 6t squared. And so I've got a 6t squared minus 2 all over t squared plus 1 cubed. And that 6t squared minus 2 we could write as a 2 times 3t squared minus 1, but I'll just leave it like this. In other words, I could factor out a 2 from the numerator if I wanted to, but we'll just leave it here. Now, what are we interested in? We're interested in everything happening at time 2. So we want to know, what is the velocity at time 2? That's given by 2e to the 4, 1 over 2 root 2, -4 over 5 squared. So there's our velocity. We're also interested in speed. So speed is the magnitude of our velocity. And this is then the square root of 2e to the 4 squared plus 1 over 2 root 2 all squared plus -4 over 5 squared all squared. So that's our speed. Maybe I'll just indicate here that this is, because I haven't actually said that this is the speed. So the idea is that the speed is the magnitude of the velocity. So whenever I write magnitude of velocity, that means speed. So I'll just indicate there that that's our speed calculation. And then we have our acceleration. And our acceleration is going to be 4e to the 4. Oh, sorry, I'm just looking up here to see what the chat is. Should be t to the -3/2. Oh, thank you. Yep, right here. I missed that negative sign that came down. Thank you. And then this is 4. Okay, so now that's 1/4, 2 to the negative 3/2. And then we've got a 6 times 2 squared minus 2 all over 2 squared plus 1 cubed. And we can simplify this thing. Let me just jot down what the final result is. I've probably pre-calculated it somewhere. Here we are. This, that it? Nope, I'm on the wrong page. And so it works out to be, we've got 4e to the 4th. We've got a negative 1 over 8 root 2, and the last one is 22 over 125. And so there is our acceleration vector. So those are the 3 things that we've just introduced now. The calculations are not new, of course. There's just derivatives. What we're doing is we're interpreting these things in a particular physical example. Now we're imagining this to be a particle. Its position function is given by r, and we're making sense of what these derivatives are and the magnitude of the derivative is in the case of the velocity vector. Okay, so let's have a look at another 2 examples. Now I just want to point out with these next 2 examples, I'll leave a little bit of room here on the top if you're still copying. These next 2 examples, they're examples that you most likely have seen before. You probably saw them in Physics 11. If you took Physics 11 or Physics 12, you probably saw them. And even in some physics classes, if you took physics, first semester physics at the university, you will have seen these classic examples of particles moving under constant acceleration. So it's not the fact that I'm doing physical examples here that's new. What I'm trying to illustrate with this is that we can get these results that we may or may not have learned in physics. So some of you might not have done some of these classes in physics, so this might not be familiar to you, but we can get these results because they just follow from differentiation. So all we're doing is we're taking the tools that we've developed in mathematics and we're just applying them to physics now, and we'll see that things fall out quite naturally. We don't need to have experience with particles under constant acceleration to actually do these calculations. We can derive these results. So in some sense, we're deriving all of the results you probably would have learned in Physics 11 and 12 to do with particles moving under constant acceleration. So let's have a look at the first example. So we want to find the position vector of a particle that has this acceleration vector. So this is telling us that the particle is accelerating or has an acceleration vector that points downward. It's pointing in the downward direction, and its value is approximately -10. Well, its value is -10. I should have said that. Its value seems to be eerily approximate to the value of g, little g, the constant or the acceleration constant of Earth, planet Earth. So you'll see that the number was chosen here to be -10, to be close to something you may or may not have seen in your physics class before. So let's start with this acceleration. We've got a of t is equal to -10 k hat. We've got a couple of initial conditions. We know the initial velocity and the initial position of our particle, and we know that it's accelerating downward at -10. Sorry, I'm just peeking at the comments here. Oh, yeah, for some reason a negative cropped in. Why did a negative crop into my final answer for acceleration? Did I miss a negative sign somewhere? So when I took the first derivative, I got v, and then when I took the derivative again for acceleration, oh, I missed the negative sign. So there is a negative sign here. right? Because down here is square root of t. If I think of it as a power, that's t to the negative a half. So when I differentiate, I will get that negative sign cropping up, which means there should be a negative sign here and here. And that explains why there's that negative sign in the answer. Yeah, thanks for pointing that out. Sorry, I did drop that negative sign. So yeah, that middle component, the j component of the acceleration, should have a negative sign in it. All right. So what can we do with this? Well, the idea is we know acceleration is the derivative of the velocity, so we can anti-differentiate to get the velocity vector. So if I anti-differentiate, I get a negative 10t k hat. So what am I doing here? We are anti-differentiating. Okay. Now the thing is, though, when we anti-differentiate, we get constants of integration. So I've got to have a plus a constant for every term that I anti-differentiate. So there's an I hat and a j hat term here that are both 0 in the acceleration. When I anti-differentiate them, I get constants there as well. So I just absorb all those constants into a vector, which I call c. And what do we know about c? Well, we have that there's some initial values that our velocity has to satisfy. So where v of 0 is equal to 0 k hat plus c. Or in other words, where c is equal to 1, 1, negative 1. So we anti-differentiate, we get our constants of integration, and then we use the initial condition v of 0 to figure out what those constants have to be. And so that tells us then that this is 1, 1, negative 1 minus 10t. There's our velocity. And well, what do we have? Well, sorry, I was about to write down acceleration again, but we're going up the chain, so we want to now anti-differentiate again to get position. So when we anti-differentiate again, I get antiderivatives of 1 is t, antiderivative of 1 is t, antiderivative of the third component is negative t minus 5t squared, and I get another collection of constants of integration, which I'll just call d. So those are more constants of integration, where r of 0, which is, I'll plug 0 in, 0, 0, 0, plus the constants in the vector d. So that means d is equal to r of 0, and r of 0 is 2, 3, 0. And so that means that our position, I'll throw those constants in here now, our position is given by t plus 2, t plus 3, and negative t minus 5t squared. And so there is r of t. So there was nothing new here in the sense of the mathematics we're doing. We are anti-differentiating. We are finding the values of the constants of integration by using the initial conditions. So all things that we've done before in previous calculus classes. We're just noticing that we can do them on all the components all at once, and we can solve these problems in physics related to constant acceleration. In fact, it doesn't have to be constant acceleration here. It just made the first integral a little easier to deal with, but we could do it for variable acceleration as well, and the same process applies. So we've basically extended the kinds of techniques that one would learn in a physics class for dealing with motion of particles under constant acceleration. Now we're able to work with motions of particles with any acceleration through anti-differentiation, and we work component by component. Okay, so let's do another example. This one is probably also familiar for those who have done physics. We got a projectile. It's being fired with an initial speed of 500 meters per second at a given angle of elevation. And we want to know a few things about the projectile. What's its range? What's the maximum height reach? What's the speed of impact? Again, for those who've done physics, nothing new with this example. You've probably done it a million times before in your previous classes. In your previous classes, though, you probably worked with components. You probably worked with the x component of velocity and acceleration, the y component of velocity acceleration, and did those calculations separately. With this example, I just want to show that we've now got the machinery, the tools, that we can work with this just as vectors themselves. We don't have to split them up into their corresponding components. We can work with the vectors as a whole. Our calculations will be done in each of the components of the vectors, but we don't have to split up our calculations and say, here's the x calculation, here's the y calculation. We can do it all as a whole. And so again, nothing new here other than just using our tools that we're developing in this course to solve problems in other areas. So a projectile is fired with that initial speed. So what we're looking at here is a projectile that gets fired and it's going to travel in some way. So there's its initial velocity, 500 meters per second, and that is happening at an initial launch angle of 30 degrees. We're interested in a few things. We want to know what is the range of the projectile, so how far has it traveled? What is the maximum height? And what is the speed of impact? So when it impacts over here, at what speed is the particle traveling? Thanks, just saw the comment about projectile curves. So what can we do? Well, the first thing we're going to do is we're going to write down what it is we know about this projectile. So we're firing this projectile, assuming we're firing it on the surface of some sort of planet where gravity is taking effect. Then the acceleration is going to be constant. And the acceleration is in the downward direction, so negative g. And since this projectile is sort of traveling along a plane, we'll just think of this as a two-dimensional motion. There's no sort of moving side to side. It's just whatever the plane is determined by the trajectory of the projectile and the sort of the vertical direction. So the x direction and the vertical direction is what we're interested in here. So this is happening in the downward direction. There's our j hat. So I'm imagining I'm throwing some coordinate axes into here. Well, actually, let me just throw them in the spot that makes the most convenient. So I'm throwing some coordinate axes in here, our y-axis and an x-axis, and I'm taking the origin to be the launch point of the projectile. So there's our acceleration. That means that our velocity we can get by just anti-differentiating. So that's negative gt j hat plus the constant of integration, and in this case it turns out to be v naught, the initial velocity. Just because if I plug in 0 for t, then that constant turns out to be the value of the initial velocity. It's v of 0. We're not really interested in velocity so much as we really want to know the position, so r of t, and so we anti-differentiate again, and that's negative 1/2 gt squared j hat plus v naught t plus r naught. And so there is our parameterization of our position function. And so you can see that that looks awfully familiar. It probably looks to you like, if you've done physics before, it looks like that 1/2 gt squared plus v naught t plus s naught, where that's just a function of a real variable in it's a real value answer. In this case, these are vectors, but the idea is that the same rule holds for all of the components in the vector. And we've stripped off the fact, maybe I'll write this in a slightly different color. We've stripped off the fact that something interesting is happening in the j-hat direction. That's where we've got acceleration going on. Yeah, I agree with that sentiment, that physics, the formulas we get in physics, they make a lot more sense once we have calculus in our toolbox, because we can see that we can derive them. We can derive these rules from physics, or these laws of physics. So what we've got here is that we've got our position function. So now I can, fill in some of the details here. What is it? V naught. So what is V naught? That's our initial velocity. So I look at my initial velocity and I say, well, the speed is 500 and it's got a launch angle of 30 degrees. So it's 500 cosine of 30 degrees and 500 sine of 30 degrees. Those are the two components that we get for our initial velocity. And so this is 500, well, it's 500 times root 3 over 2. So that's 250 root 3, and it's 250 for the y component of our velocity. And in this next one, we needed to know what r naught is, but r naught is just the initial position, and we've taken our coordinate axes to originate at the launch point, so this is going to be 0, 0. And so now we've got all the information we need in order to sort of fill in what this is. This is 250 root 3 and 250, oh, so I've missed my t there because it's v naught t, so it's 250 root 3 t. That's coming from the first component of v naught times t. And then we've got 250 t minus 1/2 gt squared. And so there is our position at any given time. And we can see that now it's parabolic. We can do a bit of a changing around of sort of the variables here. In other words, I can take the y, which is currently expressed as in time, and the x expressed in time. I can eliminate the variable t and write y as a function of x, and I'll see that y is parabolic. Y is a parabola in terms of x, and that gives us this parabolic trajectory. So those are the kinds of things we can see from this expression, but this gives us the full information about this curve. Now, what kinds of bits of information do we want to figure out? We want to know what the full range is. So the thing to keep in mind is that the range is where the particle hits a height of 0 again. It starts at height 0. I want to know where it hits height 0 again. So we want to find, maybe I'll change this because now I'm going to change the color because we're now starting to answer the questions that are given. So we want to find t such that the y value is 0. So that's 250t minus 1/2 gt squared is equal to 0. And there's two solutions to this. There's a t equals 0 solution. And that's just because it started at height 0, so we can't miss that one off. And then the other one is we can solve for t as well, and we get a 500 over g. So those are our two values. This is the initial, and this is the end. Ran out of room again. I'm going to move that over slightly. So, and that's the end. That's when it finally touches down again. That's time 500 over g units of time later, or seconds later. So now we can go ahead and say, what is the range of the projectile? Well, we know the time of travel now, so the range is just going to be the x value at that time of travel. So the x coordinate at t equals 500 over g, and that's given as x equals 250 root 3 times 500 over g. And that's meters. So that's the range that it's traveled. What's next? We want to find the maximum height. So max height, there's a couple of ways you can do this. One way is you could just say, well, the maximum height occurs halfway along its travel. So take t and divide it by 2. But I'm going to do this in a more calculus kind of way, where I say the max height occurs when Vy, so the y component of the velocity, is 0. Because when it's at its maximum height, it's at a point where the velocity in the vertical direction is 0. It's not changing in the vertical direction in some sense. It's come to a temporary halt. It's not changing, it's not increasing in height, it's not decreasing in height. It comes to a temporary halt. So that's where its y velocity is 0. And that occurs, I look back up at my velocity function and I see these components. So I have to circle the v naught part of it as well. It's when those things, negative gt plus 250 is equal to 0. Or in other words, where t is equal to 250 over g. In other words, it's half of the time, or you hit your maximum height at half of your flight time. And so that means that what is our maximum height? It's going to be the x value, or the y value at that point. So y at t equals 250 over g is, that's our max height, and that's going to be 250 over g. So I'm just filling in 250 over g for the various variables t. And whatever this works out to be, well, we can simplify it a little bit. So it's 250 squared over g minus 1/2 250 squared over g. In other words, it's 1/2 250 squared over g. Scroll up a little bit and fit that in. So it's going to be 1/2 250 squared over g is our maximum height. Next is we want to find the speed at impact. So the speed at impact means we need to know what is the velocity at that final time, 500 over g, and the velocity in this case is 250 root 3, 250 minus 500 over g times g. So that's just plugging the final time 500 over g into our velocity vector function. And in this case, it becomes 250 root 3 and negative 250. A little bit of room there. Negative 250. And that has a magnitude of, well, you can see sort of what happened. If I look at these last two components, I see that at this point, my final velocity is in this downward direction. It's still got the same x component that I started with. It's still, because there's, the key point here is that whatever its initial x component of its velocity was, that's going to remain throughout, because the only thing that's affecting its motion is this downward force. There's no horizontal force here. There's no air friction or anything. So its horizontal velocity is going to remain constant throughout its motion. It's only the vertical velocity that's changing, and that's now at negative 250. It started at positive 250, now it's negative 250. So it's still traveling at 500 meters per second, and it's just now happening in the downward direction. I need to get that per second in there. There we go. It's just happening now in the downward direction. So our final speed at impact is still 500 meters per second. Okay, so again, with this example, it's not that I'm not teaching you physics here. I'm not showing you something that you haven't seen before if you've been in a physics class. I'm just showing that all those results that came about in physics for motion of particles with constant acceleration, they're just coming from calculus, and in fact we can do them by working with vectors instead of their individual components, separating out calculations, which is what one would have typically done in, say, a physics 11 or physics 12 class. One would say, here's all my calculations to do with the horizontal direction, here's all my calculations to do with the vertical direction. Now we know about vectors, and so we can just use vectors to keep track of those things. G in this example is the acceleration due to gravity. So this is accel due to gravity. And if we're talking about Earth, this is about 9.8 meters per second squared. So that's what little g represents. So Earth, it's about 9.8 meters per second squared. And because it's happening in the downward direction, we're taking it to be negative, so it's negative g. Just like in the previous example, I sort of indicated that 10 seems to be eerily close to 9.8. And so this was just an example where we also had a particle that was under the influence of gravity that was eerily a lot like Earth. All right, let's have a look at the next the next concepts. So the idea with this next little bit is to make sense a little bit more about what acceleration is and how it can break down in terms of space curves when you've got an object. So imagine you're on a roller coaster and you're traveling. The roller coaster starts to maybe speed up as you come down the hill. So you're noticing acceleration because there's a change in speed. But at some point, the cart you're on is probably traveling at a constant speed. It's just the feelings that you're getting are because you're going around turns. So you're also feeling an acceleration due to a change in direction. And that's what we want to capture here. We want to get across the idea that acceleration can come in sort of two flavors. It can be because your velocity is changing, or it can be, or maybe I should say it this way. It's always because your velocity is changing. That's the definition of acceleration. But you can feel acceleration, or you get an acceleration because either your speed is changing. In other words, you get an acceleration because the magnitude of your velocity is changing, or you get an acceleration because the direction that your velocity is pointing in is changing. Because velocity has two elements to it as a vector. It's got a magnitude and it's got a direction. And your acceleration can be broken up into those two components. It could be because your magnitude of your velocity is changing, in other words, your speed is changing, or because the direction of your velocity is changing. And those are what we're going to be calling tangential and normal accelerations. But in order to talk about those, we have to be able to talk about direction of velocity, direction of acceleration. And so that gives rise to this tangent vector, because that's giving us a direction that's very naturally associated with the curve of motion. But there's also going to be another vector that we're going to have to get a feel for, and that's a vector that's perpendicular to the tangential direction. That's what we're going to call the normal vector, and we're going to see very quickly how we can calculate these things. So the first part here, tangent vector, these are all going to be units, so length 1. So what is the tangent vector? The tangent vector to a curve is just the derivative, r prime, over its magnitude. So that's the unit part of it. But now that we've got interpretations of what r prime is and the magnitude of r prime is, we get that it's the velocity vector divided by its speed. So here, we use v without the vector on top to indicate the magnitude of the velocity, and that's what we're calling speed. So that's how we get our unit tangent vector, is we take the velocity vector and we divide by its length, or we divide by speed. The normal vector is the vector divided by the derivative of the tangent vector divided by its magnitude. So why is that? Well, recall that, so what, maybe I should say, why is this normal vector perpendicular to the tangent vector? Well, let's recall something. Recall that the dot product of t with itself is, sorry, not 0, I'm getting ahead of myself, is 1. Why is it 1? Because t is a unit vector, since the magnitude of t is 1. And so we've got that the dot product of t with itself is 1. So that means now we can differentiate this. These are functions of t. So when I differentiate, what I get is that this side becomes the derivative of the first dot the second plus the first dot the derivative of the second is equal to the derivative of 1, which is 0. But due to the fact that the dot product is commutative, this is really just 2 times t prime dot t. And that means then t prime dot t has to be 0. Since twice it is 0, it means that the dot product itself is 0. And that means that t prime is perpendicular to t. So that's great because we found a vector that's always perpendicular to t, the tangent vector, no matter where we are on the curve. And so this thing is always perpendicular to the tangent vector. So if I normalize it, divide by its length to construct a unit vector, then now I've got a vector that's normal to the curve at any point along the curve. So I've got a tangent vector now along the curve, and I got a normal vector along the curve. So I got 2 vectors. Anytime I'm traveling along the curve, I've sort of got these 2 vectors that are always perpendicular to each other. One points along the direction of the curve, the other one points normal to the curve. So that's quite nice. So I've got a picture that sort of looks like this. I got a tangent vector, and I've got a normal vector, which are perpendicular to each other. And that's at every point along the curve. So with that, we can now go to our discussion about acceleration. So how does acceleration sort of break down? Well, let's work out what it is. So the velocity is given by, so maybe I should say what's written here. The components of acceleration. This tells us that the acceleration vector can always be written in terms of, or as a linear combination of, the tangent vector t and the normal vector n. And it's made up of a linear combination of those. So there's some weighting in front of the tangent vector and some weighting in front of the normal vector. The weighting in front of the tangent vector, this bit here, that's what we call the tangential acceleration. And it turns out that it's just related to the derivative of speed. So it's how the speed is changing. Whereas the piece that's in front of the normal vector, that weight, that's related to how the acceleration you get due to changing direction. And so that's, as shown in the next line, that's given by the curvature and the square of the velocity. So let's see why this is the case. I want to derive this formula here. So the first thing I'm going to do is I'm going to start with the fact that velocity is equal to the magnitude times the direction. So this is a way we can break down what velocity is. It is, the velocity vector is just the vector that points in the tangential direction and has magnitude, which is absolute value or magnitude of v. So that is worth noting. So where v, that should be a vector because it's a magnitude, is speed. Okay, so I've just written the velocity vector as speed times the direction it's pointing in. Now what I can do is I can take its derivative. So what's acceleration? That's the derivative of that. And what's the derivative of this? It's going to be the product rule. So it's the derivative of the speed, which we'll write in this way. I'm going to actually move something over because I'm going to insert something which I've already indicated before. We'll just write this as Vt, where V without the vector head denotes speed. So that's just the magnitude. And that means that this next line I can simplify a little bit. I could say, what's the derivative? It's the derivative of the first, which is V prime times t, plus the first times the derivative of the second. So there's acceleration. We just get it from the product rule. And now we can see already that the tangential acceleration is just the derivative of the speed. That's the V prime part. Now we also need to get this other part of the acceleration, which is in the direction of t prime. But we know from above that t prime, so let's just jot it down here. What is t prime? Well, t prime is the magnitude of t prime times the normal vector. Right? So all I did was said, here's my definition of n. So if I move the magnitude, which is on the denominator of the right-hand side, and I multiply both sides by that, so I move it over so it's sitting next to n, then I got an expression for t prime. T prime is the magnitude times n. And then I can say, well, what is t prime? The magnitude of t prime. Well, the thing to note here is that we'll recall that curvature is given by t prime, and here I'll put the t's in just so we know what we're differentiating with respect to, over r prime of t. That was a formula we had for curvature. It was how the tangent vector is changing, and if we don't reparameterize in terms of arc length, we can compute it by t prime of t over r prime of t. And so that tells us then that the magnitude of t prime of t is the curvature, I'll write that down a little bit lower here, is the curvature times r prime of t. But r prime of t, that's just velocity. But that's a magnitude, so that's just speed. So what we have is got all these expressions that we've just been rewriting. We get that velocity is given by, or sorry, acceleration is given by v prime times the tangential direction, plus we've got v times another kappa v, or curvature times v. So that's our v squared times curvature, and that's in the n direction. And so that's what our acceleration can break down into. So we've got a way now to think about acceleration. Acceleration can be broken down into a tangential acceleration, which is given by the change in speed, but it's also, you get acceleration due to changing directions. And changing direction comes from the fact that it's related to the curvature of the curve, because the curvature is how the direction is changing. But it also depends on your velocity, because if I go around a sharp corner with a low speed, I don't feel an acceleration as much as I would if I'm traveling around a corner at a high speed. So it's related to its velocity as well. And so that's the normal acceleration. Next day we will do some formulas that allow us to compute what these a_n's and a_t's are in terms of the original curve. And then we'll do an example, and then we'll get into the chain rule for multivariable functions.